Let's review some of the reactions we covered in this chapter. So we're going to start with a carboxylic acid reacting with thionyl chloride. The next reaction involves a carboxylic acid and phosphorus tribromide. The third reaction involves a carboxylic acid and adding base and an alkyl halide, or we could do a similar reaction with ACl and an alcohol, which would be the Fischer esterification. And then lastly, we have DCC and an alcohol. All of these three variable or related reactions would give the same product. In the last reaction in the slide, we have a carboxylic acid, an amine, and DCC. In the first reaction, we're reacting a carboxylic acid with thionyl chloride, which typically converts hydroxyl groups, whether on an alcohol or a carboxylic acid, into a chlorine. So in this reaction, we'll get an acid chloride as a product. Phosphorus tribromide will convert a hydroxyl group into a bromine. If we start off with a carboxylic acid and we add any of these reagents, we can make an ester from it. So in the case of the first reaction here, we have a base that would deprotonate the carboxylic acid, which can then do a substitution reaction on the carbon with the leaving group to add the ethyl group on the oxygen. With HCl and an alcohol, ethanol, we'll be doing a Fischer esterification, which means the alcohol will replace the hydroxyl group to give us again this ester. And DCC can join ethanol and a carboxylic acid to make an ester. DCC can also be used to join an amine and a carboxylic acid and form an amide, as shown here in the product. If we add a carboxylic acid to a base, we're going to deprotonate that carboxylic acid, which will make it into a better nucleophile. And then in this reaction, we're adding an acid chloride as an electrophile. In the next reaction, we're adding lithium aluminum hydride to a carboxylic acid. In the next reaction, letter G, we're reacting lithium aluminum hydride with an acid chloride or an acid anhydride. And then lastly, adding acid or base and water to an ester or an amide. If we add sodium hydroxide to a carboxylic acid, it should deprotonate it, making it a better nucleophile, which should then attack the carbon with the halogen leaving group to make an anhydride. If we add lithium aluminum hydride to a carboxylic acid, we should get a primary alcohol. Lithium aluminum hydride will reduce an acid chloride or an anhydride into a primary alcohol as well. Sodium hydroxide or ACl plus water will lead to the hydrolysis of an ester or an amide. For most esters and amides, we usually also have to heat the reaction, although it's not shown in this particular example. Ethanol is added to an acid chloride or an acid anhydride to form the same product. And in this reaction, the next one, we have ACl and ethanol, or we can use sodium ethoxide to react with an ester. An acid anhydride or chloride can react with an amine to give the same product. And then lastly, we're going to react an amine, primary amine, with an ester. If we add ethanol to an acid chloride, we should get an ethoxy ester, as shown in this reaction. The same reaction would occur if we add ethanol to an anhydride. Adding ACl in an alcohol to an ester should lead to a transesterification reaction, so the methoxy group will be replaced by an ethoxy group. The conjugate base of the alcohol that we want to add can also be added to an ester to do a transesterification reaction as well. A primary amine will add to an acid chloride or an acid anhydride to make an amide. So the nitrogen adds to the carbon with the leaving group, giving you an amide bond. Notice the product has the same methyl group as the reagent. Methylamine can also add to esters to give you amides, as shown by this last example. In this first reaction, we're going to add two equivalents of a methyl organolithium or a methyl Grignard to an acid chloride or an ester. In the next reaction, we're going to add a cuprate to an acid chloride. Next, we're going to add sodium borohydride to an acid chloride. In the next reaction, we're adding lithium aluminum hydride to an ester. And then lastly, lithium aluminum hydride will be added to an amide. Methyllithium or a methyl Grignard will add to an acid chloride or an ester, and generally they add twice to give you a tertiary alcohol. So we're going to add two methyl groups in this example to the carbonyl to turn it into a tertiary alcohol. A Gilman reagent will transfer the methyl group or whatever other alkyl group we have and replace the halogen on an acid chloride to give you a ketone. Sodium borohydride will reduce an acid chloride into a primary alcohol. Esters and amides typically require a more reactive hydride reagent like lithium aluminum hydride. Lithium aluminum hydride should convert an ester into a primary alcohol. When it comes to amides, we typically get an amine since the oxygen is a better leaving group than the nitrogen. Once we reduce the carbonyl once, that alcohol that forms typically is eliminated by the nitrogen and eventually reduced again into an amine. Here we're going to attempt the synthesis example, starting off with an alkene which has 1, 2, 3, 4, and 5 carbons, and convert it into an amide which has 1, 2, 3, 4, and 5 carbons, plus the two methyl groups on the nitrogen. In this synthesis, we want to make an amide, which we can make from a number of acid derivatives, including carboxylic acids. And as we know, carboxylic acids are products of the oxidation of primary alcohols. And then primary alcohols, we learned earlier this semester, they can come from alkenes. So hydroboration in an alkene typically gives you anti-Markovnikov addition of an alcohol, and then that primary alcohol can be oxidized with chromic acid to give you a carboxylic acid. And then doing one of the reactions we learned in this chapter, we can convert a carboxylic acid into an amide by adding an amine and DCC.